Hi everybody, welcome back. This is Unit 7, Lesson 1, and we're going to talk about the behavior of gases in this section of Unit 7. And we have a model that explains the behavior of gases. It's called the kinetic molecular theory. Okay, and it has different parts to it, but in order to introduce you to those parts, I thought I would let you hear a little rock video. So here you go, enjoy. Whoop, let me try again.
Gas is made of molecules that are far apart and small. They don't lose their energy when they hit container walls. They travel in a straight line, no changing from their course. They move faster when it's hotter. They have no attractive force. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. Gases that behave like this are often called ideal. Which gases are most like this, though they are very real? Hydrogen and helium, the smallest gases on the chart. High temperature, low pressure, will spread them far apart. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. Assume all gases behave like this, treat them all the same. It's Avogadro's hypothesis, they've given it a name. Equal volumes of different gas, if they have the same T and P, will have the same number of molecules of gas in each, you see. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. The mass of each gas molecule is weighed in AMUs. We need to turn that mass to grams, which we can better use. You need Avogadro's number. That's something that we've heard. A mole is 6.02 times 10 to the 23rd. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. Because we treat each gas the same, each one that's on the list. Real gases have attractive force, pretend they don't exist. We can use the gas laws with each and every one. So go get your calculator out and prepare to have some fun. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. Whether you use Boyle's Law or Charles or Gay-Lussac's, you can use them on any gas. You won't get no flack. Thanks to Avogadro, we can treat them all the same. And that is why I wrote this ditty in honor of his name. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. Rock me, Avogadro, rock me, Avogadro, rock me, Avogadro, with gas laws. P1V1 over T1 equals P2V2 over T2.
Alright, so if you didn't catch it in the music video, there were some key important points about how gases behave. And the first one is how they move. So gases, when you could put on your Miss Frizzle glasses, and if you could look at the individual atoms or molecules that make the gas, the molecules are moving in constant, random, straight line motion. So they don't move in waves, they move in straight lines, and it's not like a gas says, oh, I'd really like to be on the other side of the room. It's just random motion until they hit something, okay? Constant, random, straight line motion. But they will hit things, they will hit each other, and they will hit the walls of their container. I know you can't see that. Let me move it up for you. So gas particles will collide with each other and the walls of their container. And when they do collide with the walls of their container or each other, they may transfer energy, but there's no net loss of energy. They hit and bounce off, hit and bounce off, hit and bounce off. So we call those collisions elastic. So when the gas particles collide with each other, they may transfer energy between them. However, there's no net loss of energy, and so the collisions are said to be elastic. Okay? This diagram that you have in your notes is trying to show you a property that gases have that solids and liquids do not have. If you notice, gases, the atoms or molecules are spread out, whereas in a liquid the molecules are very close together. So what you can do is really you can smush a gas. You can smush those particles closer together, where you cannot do that for a liquid or a solid. Smushing has a more scientific word. It's called being compressible. And, oh, I didn't spell that right. The reason they're compressible is because the particles of a gas are separated by huge distances. They're really spread out. In fact, most of a volume, let me write in a different color here so you can see what I'm writing. Most of the volume of a gas, just like most of the volume of an atom, I thought I hit a different color, is empty space. Feeling blue today. And so what that means, if most of the volume of the gas is empty space, and you should be flipping over to your second page of your notes, what we say is that the gas particles themselves have no significant volume. The volume of a gas is really represented by the volume of the container. So the gas will spread out and occupy the container that it's in. How about purple now? Oh, didn't work. Oops, sorry. The volume occupied by the particles themselves is negligible, which means not important, okay, and need not be accounted for. And what we're really saying when we say this is that gases take the volume of their container. Okay, so again, gases have a volume that's insignificant. It's not important. They take the volume of their container. So if you exhale into a 5-liter container, your exhalation will spread out and occupy the whole 5 liters, even if you only exhaled a little bit of air. Okay, and the volume of a gas particle itself is insignificant. All right, gases do not attract or repel each other. They have no forces of attraction, right? We learned that in our bonding unit, that gas, actually we learned it in our very first unit. They have no forces of attraction. Ideally. In reality, they kind of do. But ideally, they have no forces of attraction. Temperature determines the motion of gas particles, or the kinetic energy. Remember, kinetic energy is energy of motion. And again, as you saw in the video, the higher the temperature, the greater the kinetic energy, the more motion there is. And I think this is the diagram that you saw in the video. You had a gas molecule at 200 Kelvin with only little vroom vroom lines, which means it's not moving as much as a gas that's at 400 Kelvin. A gas at 400 Kelvin has twice the vroom vroom lines, or twice the kinetic energy of a gas at 200 Kelvin. Greater temperature, greater kinetic energy, okay? If a gas follows all these rules, we say that it is ideal. An ideal gas is a gas that is a rule follower. It follows all the rules of the KMT. Most gases, let's just look at, let me put up a little screen shade here. Sean's copying all the words down all together. But let's just talk about ideal gases first. This is really important. It's an important concept. Ideal gases versus real gases. Ooh, that's not what I wanted to do, but that looks pretty cool. Okay, So ideal gases obey all the laws of the KMT. You're going, what the heck's the KMT? That's those little bullets that we just listed, right? The way that gases should behave. Most gases will behave these rules when they're spread out. So when the temperature is high and the pressure on them is low, then most gases will behave ideally. And the gases that will behave ideally under nearly all conditions are the lighter gases, which are hydrogen and helium. However, just like most of you are ideal students, you do what you're supposed to do most of the time, in reality, there are times when you're not an ideal student. Like, I don't know, when you don't turn in your charts, or when you don't watch my videos, or when you don't do your labs, okay? Those are real gases. They break some of the rules. Okay? One of the rules they break is they actually start to attract each other. And they actually start to take up space. Uh-oh, can't get it back. Oh, wrong button. There we go. So they'll attract each other and they'll take up space. We'll deviate the most when we're being smushed. So when we're cold, when the temperature is low, and when the pressure on us is high, a real gas will deviate from ideal behavior. And heavier gases also, and polar gases will, so funny, will behave more like real gases because they begin to have attractions. So the way that you deviate from being an ideal student is by not doing your work when you're supposed to, or maybe by not listening to me. But the way that gases deviate from ideal behavior is they start to attract and they start to take up space. Heavier gases do that more than light gases, and gases do it when the conditions are low temperature and high pressure. That's when a real gas deviates from ideal behavior. So what I do to remember this, because it is hard and confusing, is that anything that causes gases to be squeezed together will cause them to deviate from ideal behavior, which are low temp, cold, right? Squeezed together here. Let me see if I can underline this. Squeezed together means that the temp is low. Ooh, Bert, it's cold. And the pressure is high. And this pressure is very important that you recognize is not the pressure of the gas, it's the pressure on the gas. So if you're squeezing the gas together by exerting pressure on it, then it starts to clump and it starts to attract, and then it behaves more like a real gas. But if the pressure on them is low, then they can spread out and bounce around the container like they're supposed to do. Okay? I think that's it for tonight, everybody. Tomorrow we'll talk about vapor pressure, and I'll give you some demonstrations on vapor pressure. Have a great night, and we'll see you tomorrow. It's Friday. Bye-bye.